All right, welcome back to part C. Um, we were going over a balancing of equations in the last segment, and basically we found that in order that you have to balance equations because of the law of conservation of matter. You can't just have atoms disappearing into nothing, and you can't have them appearing out of nowhere, and you can't be switching elements from one atom or atoms from one element to another. So the only way that we can make chemical equations work out is by changing the numbers of molecules of reactants or products involved in order to make the total number of atoms of each element come out the same as they were going in. Again, the atoms can rearrange themselves and combine into different molecules, but you have to have the same number of atoms of the same elements in total coming out as you had going in. And the way that we balance the reactions is essentially by putting coefficients, that is numbers, in front of the chemical formulas for some of the reactants or products as needed in order to make everything work out. And the coefficient, remember, applies to the entire chemical formula that follows it. So for instance, 3 CO2s means not only 3 carbon atoms, but 6, 3 times 2, 6 oxygen atoms. When balancing equations, we normally want to use the smallest whole number coefficients possible without changing the ratios. So, in other words, 2 to 4 is the same as 1 to 2. So out of those, we would prefer to use 1 to 2 rather than 2 to 4. But we do need to have all of the ratios remain the same. And just as a reminder, you can't change the coefficients in a formula in order to make the equation balance. Once we've decided what the reactants and products are, that formula corresponds to that compound, and changing the subscripts would change the identity of the compound. So if we need more carbon, or so basically if we need more carbons in this equation, we can change the number of CO2s, but we can't change the subscript on the carbon because CO2 is carbon dioxide, and that is one of the products in the reaction. Okay, so once you've decided what the formulas for the reactants and the products are, from that point on, you can't change the subscripts anymore. If you need to change the number of atoms of an element, you can only do that by changing the coefficients in front of the formulas. So, and what we mean by the smallest whole number ratio is, for example, if you come out with an equation 4 H2s plus 2 O2s yield 4 H2Os, obviously, if you look at the coefficients here, they can all be divided by 2. Which means those are not the smallest possible whole numbers that will maintain the same ratios. So if all of the coefficients can be divided by the same factor, then you do that. And in fact, you do your best to divide by the largest possible common factor between them. And in this case, they're all divisible by 2. So we divide by 2 and we come up with 2H2 plus 1 O2 yields 2 H2Os. These are the lowest whole numbers that will give you the proper ratios in that equation. Okay. The coefficients represent the relative number of molecules or moles of one substance versus another in a reaction. Reactions can be done with any number of moles or molecules you want, though. So when we say 2 hydrogens and 1 oxygen will yield 2 water molecules, you don't necessarily have to do this reaction with 2 molecules or 2 moles of hydrogen. You can do it with any amount of hydrogen you want. What it tells you is, however many hydrogens you put into this reaction, you're going to get the same number of water molecules out at the end, because the ratio of water to hydrogen is 2 to 2, or which is the same as 1 to 1. It tells you that however many hydrogens you start out with, you only need half as many oxygens to react with them in order to form water. So that's what the 2 to 1 or 1 to 2 ratio means. It doesn't necessarily mean that you have to have 2 moles of hydrogen and 1 mole of oxygen. It just means that the ratio is 2 to 1. So if you start out with, I don't know, 14 moles of hydrogen, that would mean that you only need 7 moles of oxygen to react. And you'll get 14 moles of H2O. So the reaction can be done with any specific number of moles you want, but then the coefficients allow the calculation of the number of moles of other substances by using a ratio. And just a quick, fairly easy example, by using the ratio of the number of moles, which is the coefficients, in other words, of one substance to another in a balanced equation, you can do questions like this. If you have 13 moles of propane, C3H8, how many moles of carbon dioxide can be produced? Well, we know the equation from above is 1 mole of propane plus 5 moles of oxygen will yield 3 moles of CO2 and 4 moles of water vapor. So if you're starting out with 13 moles of propane, and assuming that you have enough oxygen to react with that, but the oxygen in reactions like this comes from the air, so you should have more than enough of that. That shouldn't be a problem. The equation tells you, though, that you get 3 moles of carbon dioxide for every 1 mole of propane that goes in. This is where the coefficients from the equation come in this ratio here. And you'll notice that the moles of propane cancel out as a unit. 13 times 3 divided by 1 gives you 39 moles of carbon dioxide coming out. Okay. You could do another one. If you have 2.7 moles of oxygen, so the oxygen supply is limited. That's unusual, but it could happen. How many moles of propane can you burn? Well, again, you just use the ratios from the equation. You can burn 1 mole of propane for every 5 moles of H2O. So if you have 2.7 moles of O2, and you can burn 1 mole of propane for every 5 moles of O2, notice moles of O2 will cancel as a unit. 2.7 times 1 divided by 5 is 0.54. That's how many moles of propane you can burn with that amount of oxygen. Again, it's a 1 to 5 ratio because 1 to 5 would be the numbers, 1 and 5 would be the coefficients in the equation once it's properly balanced. To go about balancing equations a little more formally, and because we never saw how to balance the equation involving propane, again, you have to do this. I'm going to skip over this part because you have to do it to make sure that you obey the law of conservation of matter. Have to have the same number of atoms of the same elements coming out as you had going in. And the method that we're going to use most in this class, at least for now, is called balancing by inspection, which is more or less trial and error. And the process of balancing is that you essentially go left to right, looking at each element you come to and making sure that it balances between the reactants and the products. So like in this equation here, the very first one that we looked at, this is pretty easy to balance without really even thinking about it, but using this process would be looking left to right and saying, okay, we have the 2 hydrogens going in and 2 hydrogens coming out. So that's okay, they're balanced. But for the oxygens, we have 2 going in and only 1 coming out. That means this equation is not balanced and we have to fix that. Since we've got 2 oxygens on the reactant side and only 1 on the product side, that means we need an additional oxygen on the product side. You cannot get that extra oxygen by making this H2O2, because remember, changing the subscript changes the identity of the compound. H2O2 is hydrogen peroxide, not water. Very different compound. The only way you can get 2 oxygen atoms out of water is to have 2 water molecules. So that's why we put a 2 in front of the H2O, and we end up with 2 oxygens. So now we've got 2 oxygen atoms going in and 2 oxygen atoms coming out. But when we did that, we screwed up the hydrogen. Now we've got 2 hydrogen atoms going in and 4 hydrogen atoms coming out. 2 water molecules with 2 hydrogens each. has 2 times 2 or 4 hydrogens. So now that doesn't balance. So we have to fix that. And that's one thing you should always do whenever you balance an equation. Once you think you've got it balanced, always go back and check to make sure that it's balanced, because it may not be. You may have thrown something else out of balance when you fixed something that wasn't balanced before. So now we've got 4 hydrogen atoms coming out, but only 2 coming in. Again, you can't change the subscript. You cannot make this H4 because H4 doesn't exist. There's no such thing. But you could have 2 hydrogen molecules or 2 moles of hydrogen. There's no reason you couldn't do that. So 2 H2s means a total of 4 hydrogens going in and 4 hydrogens coming out. And we've still got 2 oxygens going in and 2 coming out, which means now the equation is fully balanced. And we're done. Okay, as I said, normally you try to balance elements left to right. One exception would be if there's an element that is by itself, that is not bonded to anything else, not in a compound, you would definitely want to leave that element for last. Because if that element is by itself, that means that you can fix any imbalance in that element without throwing anything else out of balance. And the way this next equation is written, you'll notice that oxygen is by itself here. If an atom of an element is bonded to another atom of that same element, that counts as being by itself. Oxygen is normally found as O2 molecules in nature, so this would count as oxygen being by itself. All of the other elements are bonded to some other element. So we would want to leave the oxygen for last in balancing. The way the equation is written, we would have come to the oxygen last anyway, but the order of reactants and products in a chemical reaction is really arbitrary. I mean, the reactants have to go on the left and the products have to go on the right, but among the reactants, we could have written this as O2 plus C3H8. We could have put the O2 first. And then we would have come to the O2 first going left to right, but we would still want to leave it for last because it's by itself. Okay, so if we're going to balance this equation, first of all, we notice that the oxygen is by itself, and so we want to leave that for last. And then we start it at the left. First element we come to is carbon. We have 3 carbon atoms going in, and we've only got 1 coming out. Well, you can fix that. Well, actually, the first thing you might want to do is check all of the elements. 3 carbon atoms coming in, only 1 coming out. That doesn't balance. For hydrogen, we have 8 hydrogen atoms going in, and we have only 2 coming out. That is not balanced either. For the oxygens, we have 2 atoms going in, and we have 2 here and 1 here. We have 3 coming out, so oxygen is not balanced either. Nothing here is balanced, so we got our work cut out for us. All right, we'll start with carbon because that's on the left and it's not by itself. We've got 3 carbons going in. We need to have 3 carbons coming out. Again, we cannot change CO2 to C3O2. That doesn't exist. But we can get 3 carbons if we have 3 CO2s coming out. And so we do that. Now we have 3 carbons going in, 3 carbons coming out. Carbon balances. Now we can check hydrogen and see if that changed. We've got 8 hydrogens going in and only 2 coming out. So that's not balanced. And the oxygens didn't change either. So they're not, oh, actually they did. So let's see if they balanced. 2 oxygens going in and coming out. We've got 3 times 2, which is 6, plus 1, which is 7. So actually, no, the oxygens are even more out of balance than they were before. So we've still got to keep going. So carbon is balanced. We would next move on to hydrogen. We've got 8 hydrogen atoms going in. We need 8 coming out. We cannot change the subscript in H2O because that would make it some other compound, but we can get 8 hydrogen atoms total out of water if we have, I don't want to write that in there because I wrote it in below, 4 hydrogen molecules. Okay, 4 times 2 is 8. And so by putting 4 H2Os coming out, we now have carbon in balance. 3 carbons going in, we still have 3 carbons coming out. So that's 3 to 3, that's balanced. For the hydrogens, we now have 8 going in and 4 times 2, or 8 coming out. That is balanced. For the oxygens, we've got 2 going in and 3 times 2, or 6, plus 4, that's 10 coming out. So we've thrown the oxygens even more out of balance. So they don't balance. So we have to fix that. Fortunately, oxygen is by itself on the reactant side. So we can do whatever, or basically we can do whatever we want to this to make the oxygens balance without throwing anything else out of balance. So let's see, we've only got 2 oxygens going in. We've got a total of 10 coming out. We need to get a total of 10 oxygens, and oxygen only comes in pairs. So that sounds a lot to me like we need 5 pairs of oxygens. And sure enough, 5 times 2 is 10. So now everything should be balanced. Carbon C3H8, 3 carbons going in, 3 CO2s with 1 carbon each, that's 3 carbons coming out, balanced. 8 hydrogens going in and 4 times 2, or 8 hydrogens coming out, balanced. 5 times 2, or 10 oxygen atoms going in. Coming out, we have 3 times 2, or 6, plus 4, which is 10 oxygen atoms coming out. So the oxygen's balanced too. If all of the elements in the reaction balance from the reactant side to the product side, then the equation itself is balanced. So that is the equation that we saw before, and we definitely saw that it was balanced. Sometimes you might end up with fractions in your balanced equation. It happens once in a while, especially when you're talking about combustion of hydrocarbons. And so you might have to use a fraction in order to get the reaction to balance. Well, you can't have fractions in your overall balanced equation because we want whole numbers. We want things that look nice and neat. Whole numbers are much easier to do or to use when you're trying to find out ratios of one thing to another, for example. So if we look at the example of combustion of butane, which has the formula C4H10, is very similar to propane. It's just that it's got another carbon and a couple more hydrogens stuck into it. Butane will burn in air, which involves the butane reacting with the oxygen, and the carbon in the butane goes to form carbon dioxide, and the hydrogen in the butane goes to form water vapor. Because this usually happens at high temperatures, the water is usually given off as water vapor, that is basically steam rather than liquid water, because the temperature is usually above the boiling point of water. And if we look at the balance where we're starting out here, C4H10 has 4 carbons. Oh, well, first of all, look for an element that's by itself, which is oxygen. So again, we want to leave oxygen until last. Given the order in which I wrote things, we would have ended up doing that anyway. We've got 4 carbons in butane, and we have only 1 carbon coming out. That's a problem, not balanced. 10 hydrogens going in and only 2 hydrogens coming out. That's a problem, not balanced. 2 oxygens going in and 1, 2, 3 coming out. That's also a problem, not balanced. What we can do, actually, I am going to do that step by step. Is we're going to start with the carbons, leave the oxygen for last, start with carbons. We've got 4 carbons going in. We need 4 carbons coming out. The only way we can get 4 carbons out of CO2 is if there are 4 entire CO2s. Okay, so now we see the carbons are balanced. Now we check the hydrogen. We've got 10 atoms of hydrogen going in, and we've only got 2 coming out. Now again, since we've decided that water with the formula H2O is one of the products, we cannot change the subscript to make the hydrogens balanced. The only way we can get 10 hydrogen atoms out of water, which contains 2 hydrogen atoms each, is if we have 5 H2Os. Now, 5 times 2, 5 waters with 2 hydrogens each would be 10 hydrogens. Okay, so the hydrogen is balanced. Now, what about the oxygen? Well, if we look at the oxygens over here, for oxygen, we've got 4 times 2, that's 8. And in water, there's 1 oxygen atom each, and we've got 5 of them. That's 8 plus 5, that's 13. Uh-oh, that's an odd number. And oxygen only comes in pairs. When something like that happens, you can just get around this by taking the number of oxygens as 13 halves. 13 over 2 times 2 is 13. Or you can think of it as 7.5. 7.5 times 2 is 13. No, sorry, 6.5. 6.5 times 2 is 13. But of course, you can't have a fraction in your overall reaction. So what do? You multiply all the coefficients by 2. Or whatever is in the denominator of the fraction. So if that were a 3, then you'd multiply everything by 3. So we end up with 2 C4H10 plus 13 O2s goes to 8 CO2s and 10 H2Os. And that should be balanced, but you always want to check. Okay, so for carbons going in, we have 2 times 4, or 8. For carbons coming out, we have 8 times 1, or 8. Carbons balance. For hydrogens, we have 10 times 2. Don't forget that 2 applies to the hydrogens in butane also. So 2 times 10 would be 20 hydrogens going in, and coming out, we've got 10 waters with 2 hydrogens each, so that's 10 times 2, or 20. The hydrogens also balance. And then for the oxygens, we have 13 times 2, which is 26. And coming out, we have 8 times 2, which is 16 for the carbon dioxide. But we also have another 10 for the H2Os. 16 plus 10 is 26. So the oxygen is balanced too. So that is your final properly balanced chemical equation for the combustion of butane. And I have the steps, well, some of the steps here. The one where we end up with the fraction. Everything balances when you have the fractional coefficient, but that's normally not acceptable for your final version of the equation. So that's why we multiply all the coefficients by 2 and to get whole numbers. The ratios have stayed the same because you multiplied all of the coefficients by 2. So actually for example, a 4-to-1 ratio is the same as an 8-to-2 ratio. That's why you can do that. As long as you multiply all the coefficients by that same number, you're still maintaining the proper ratios and the equation will remain balanced. Okay, there's other information that we can convey in a chemical reaction. Things like the physical state, we've already seen this to some extent. The physical state or phase of chemical substances. These are also known as phase labels, and that's the little S in parentheses for a solid, or L in parentheses for liquid, or G in parentheses for a gas, or AQ in parentheses if the substance is dissolved in water. That stands for aqueous, which means dissolved in water. And those would be like little subscripts that follow the formulas for the compounds. And so, for example, when we write the reaction for forming water from hydrogen and oxygen, we get 2H2 gas plus O2 gas will produce 2H2O liquid. Or 2C4H10, that's butane gas, plus 13O2 gas will produce 8CO2 gas and 10H2O gas. Try to get off the gases here. Acid-base reaction, the base NaOH, which is dissolved in water, so it's NaOH aqueous, will combine with hydrochloric acid, which being an acid has to be dissolved in water, so that's aqueous also, will result in sodium chloride, which is dissolved in water or aqueous, and liquid water, which technically is also dissolved in water, but aqueous water would be kind of redundant, so we call that H2O liquid. H2O will always be solid, liquid, or gas, but you will never see H2O aqueous because that's kind of obvious. Of course, the water is dissolved in water. You can denote heat application if it's required for the reaction to go forward as a triangle or the capital Greek letter delta over the arrow. So triangle over the arrow, that means heat must be applied. So in order to take calcium carbonate solid and break it down into solid calcium oxide and gaseous CO2, you need to apply heat. Okay. And at that point, I see we seem to be at the end of our time for the third segment of our lecture. So I will call it there. And we'll continue with ionic equations next time.